All right, hi folks, I'm recording a video for section 4.1, and this is dealing with polynomial functions. So let me work through a few examples from my math lab. And the first one here is asking us to form a polynomial whose zeros and degree are given. First, let me explain what the degree of a polynomial is. So let me give you a couple of examples of polynomials. So here is a polynomial function. I'll just make up an example. Let's say 5x to the 4 minus 6x to the 3 plus 2x squared minus 4x plus 9, let's say. All right, you'll know this is a polynomial function because all of the exponents here are positive whole numbers. Okay, so for a polynomial function, these exponents on all of these x's must be positive whole numbers. If the exponent was a fraction, it would not be polynomial. If the exponent was a negative number, it would not be a polynomial function. All right, well, for this kind of a function, the degree is the highest exponent that appears, assuming we just have a variable x. So the degree is the highest exponent that appears. Well, in my example, the highest exponent is 4. So in this example, we would say this polynomial function is degree 4. All right, now, one other bit of terminology. If you look at this first term that contains that highest degree, it's 5x to the 4. We call this the leading term. So the term that contains that highest exponent is called the leading term. And this is important because we're going to analyze the leading term to get information about the behavior of this polynomial function. All right, well, let's go to this example. It says, form a polynomial whose zero and degree are given. First of all, they're telling me degree 3. So that means my function that I want to create has to look something like an x to the 3rd in it, because that'll mean degree 3. All right, it's also mentioning that the zeros are -4, 4, 6. Well, what is a zero? Well, if you were to think of the graph of this function, a zero is really the same as an x-intercept. So you can think of zeros and x-intercepts as one and the same. A zero really means where is the y value equal to 0 for the function. So these zeros are the x values where y equals 0. So if I was to draw these zeros, here's -4, here's +4, and here's +6. So I'm going to put a blue dot at these x-intercepts because I know the graph has to pass through these points. And if I was to write the xy coordinates for each one of these points, this would be -4, 0. This would be 4, 0. And this would be 6, 0. Notice how for each one of these x-intercepts, the y value is 0. That's why we call these numbers zeros. Okay? And so the graph of this function, I really don't know exactly what this looks like. At this point, we are going to talk about graphing polynomial functions, but I do know that the graph must pass through these 3 x-intercepts. All right, well, here's the way to set this up. What I'm going to do is write this as 3 parentheses. And the reason I'm going to use 3 parentheses is I know the equation is degree 3. And the way you write this is x minus the 0. So this is going to be the first 0. And then I'm going to write it as x minus the second 0 and x minus the third 0. And again, the reason I know to write it with 3 parentheses like this is I was told that this is degree 3, and I was also given 3 zeros. Okay, now usually there's a leading coefficient here in front, and I'm going to use an A here to mean the leading coefficient. But now I want to plug in the numbers they're giving me in my problem here. They're telling me I should use a leading coefficient of 1. So really this A number is 1. If they had told me to use a leading coefficient of 10, I'd be replacing A with 10. Now I'm going to drop in the zeros. Well, it's going to be x minus, the first 0 is a negative 4. X minus the second 0 is a 4, and the third 0 is a 6. All right, well, I'm going to write this one more step because I just want to clean up this x subtract a negative 4 here. You know, anytime I have x subtract a negative number, I can rewrite it as x plus 4. So this is the polynomial function they're asking me to generate. And I could multiply these parentheses out if you wanted to, but this is the setup to form the polynomial function that they're asking us to generate here. All right, let me go to another example. Let me go here. Now this is similar to the example we just did, but it introduces something called multiplicity. So again, notice they're telling me here this is degree 3, and they're giving me zeros, but they tell me it's going to have multiplicity. All right, now I'm going to write the setup just like we did in the problem from just a second ago. So I'm going to write this function again as f of x equals a. A is the leading coefficient. And because it's degree 3, I'm going to write it as x minus the first 0, x minus the second 0, and x minus the third 0. Okay. All right, now let me talk about multiplicity. Multiplicity means how many times does that 0 appear in the function? Because a certain 0 may appear more than once. All right, well, if it says multiplicity 2, what that means is that 0 shows up twice. All right, well, I'm going to start filling in then for my problem. They told me the leading coefficient was 1, so I'm going to replace a with 1. Okay. Let me take the first 0. The first 0 they're giving me is negative 9, and they're telling me multiplicity 1. Well, that means that 0, negative 9, shows up just one time. So I'm going to write it as x subtract a negative 9. Let me go to the next 0. The next 0 is a 3, but they're telling me multiplicity 2. Multiplicity 2 is indicating that that 0 of 3 really has to show up twice. So I'm going to write it as x minus 3, x minus 3. So multiplicity is really telling you how many times the 0 appears in this factored form of the function. All right, let me just clean this up a little bit, because in this first parenthesis, x subtract a negative 9, of course, that's going to flip to be x plus 9. And then if I wanted to, usually the way we would write this is if I have the parenthesis x minus 3 times itself, I could write that as the quantity x minus 3 to the exponent 2. So this is the typical way to write that kind of this kind of a polynomial function. All right, and again, I could multiply this out to get the expanded version of that polynomial function. All right, let me go to another example. Let's see here. Let's go to an example here. All right, so again, this is asking me to set up a polynomial function, and it's giving me the zeros and their multiplicities. And it's also giving me that the function is going to be degree 4. Remember, that means I'm going to have an x to the 4 in the function. And it's also giving me an xy point 2 comma 40. So they're giving me 2 comma 40. So this graph, if I was to graph this function, the graph would have to pass through the point 2 comma 40. Notice they're not telling me here that the leading coefficient is 1. In the previous examples, they said, assume the leading coefficient is 1. They're not telling me that here. All right, let me set up the polynomial function just as we did previously. So let me write this as a times x minus, I'm just going to write z sub 1 here for the first 0, z sub 2. Let me actually write it a little better. So I'm going to write it as z sub 1, z sub 2. Whoops. Remember, these are going to be each one of the zeros. And I know to put 4 parentheses here because they told me this function is degree 4. All right, now I'm going to fill in these zeros. And of course, I have to keep in mind the multiplicities. Multiplicity, remember, is how many times that 0 should appear. All right, well, I have to leave a by itself because I don't know the leading coefficient yet. All right, let me go to the first 0. It's a -3 with a multiplicity of 1. All right, so I'm going to write this as x minus a -3. Let me go to the next 0. The next 0 is a 1 with a multiplicity of 1. So I'm going to write that as x minus 1. Then I'm seeing that the next 0 is a 4, but this has a multiplicity of 2. So that means I have to write x minus 4 2 times. Okay, so x minus 4, x minus 4. All right. Now, in the first parenthesis, I know that when I have x subtracted -3, I can really think of this as x plus 3. All right, the one thing that's missing in this analysis is this leading coefficient. So how can I find the leading coefficient? Well, they gave me this xy point, and it turns out this xy point can be used to figure out that value of a. Here's the way I'm going to do it. Instead of f of x, I'm going to think of this as the y variable. Remember, f of x and y are interchangeable. So then I'm going to have y equals a, x plus 3, x minus 1, and then usually I'll write this x minus 4 times itself twice using the exponent 2. All right, now to find a, what I'm going to do is replace x with the number 2 and replace y with the number 40 in this equation. If I do that, the only unknown is the a, that leading coefficient a. All right, so I'm going to do it. Y is a 40. A is unknown. I'm going to replace x with 2. So this is going to be a 2 plus 3. This is going to be a 2 subtract 1. And this is going to be a 2 subtract 4 squared. All right, now I'm just going to work out these parentheses. This is going to be 40 equals a. This first parenthesis is 5. The second parenthesis is a 1. This third parenthesis is a -2 squared. Right, that's going to be a -2 squared. which is 4. All right, so it looks like I have 40 is equal to a times 20. And to get a by itself, I'll divide both sides by 20, so it looks like a equals 2. So now it looks like this number a is going to equal 2. All right, well, this one is a multiple choice question. So let me see which answer matches up to my result here in this blue box. Well, it looks like I'm noticing answer A and B are no good because they have a -2 in front, but that's not correct. Our A turned out to be a +2. And I'm noticing answer D is incorrect because they forgot to put the exponent 2 back here on this x minus 4. So it looks like the only answer that makes sense here is answer C. So answer C matches up to the polynomial function that we came up with here. All right, let us look at maybe one more. And this problem is a little different because in this problem, instead of you constructing the polynomial function, here they're giving me the polynomial function and they're asking me to do some analysis. All right, let's work through this one step at a time. All right, the first step is they're giving me this function and they say, what are the zeros of this function? Well, remember, when you see the word 0, you can think of x-intercepts. So another way to think about this question is, what are the x-intercepts? Well, for the x-intercepts, you let y equal 0. That's the way you find x-intercepts. So let me take this function that they're giving us, and I'm going to replace y with 0. Of course, that means replace f of x with 0. Remember, f of x and y are interchangeable. So that means I'm going to end up with the equation 0 equals -7 x minus 5 times x plus 3 squared. All right, but anytime you have quantities being multiplied equal to 0, you could set each one of the quantities separately equal to 0. So I'm going to do that. I'm going to set each one of these quantities separately equal to 0. I'm going to set that quantity equal to 0, that quantity equal to 0, and that quantity equal to 0. Of course, I'm not going to bother really setting -7 equal to 0 because that's no solution. But I am going to set x minus 5 equal to 0. And if I set x minus 5 equal to 0, I'm going to, of course, get the answer 5. So x equals 5 here. All right, how about x plus 3 squared equals 0? Well, the only way x plus 3 squared can equal 0 is if the quantity inside the parenthesis equals 0. So I'm going to set this to be x plus 3 equals 0. That gets me x equal -3. Okay, so those are the zeros of this function. And again, you can think of it as the x-intercepts. So I'm going to type in here 5, -3. All right. Let's go to the next question about multiplicity. Well, remember, multiplicity is how many times does the 0 appear in the function? Well, really, you can use the exponents to tell you multiplicity. So if I look at this function, on this parenthesis x minus 5, I can think of it as exponent 1. So this is going to have a multiplicity 1. Remember, the 0 for this was 5. So this parenthesis is a 0 of 5 with a multiplicity of 1. Because I can think of that exponent on the parenthesis is telling me, so this is a multiplicity of 1. I can think of that exponent on the parenthesis is telling me the multiplicity. All right, what about the second parenthesis? Well, we know the 0 here was -3. We just figured that out a second ago. But the exponent is 2. So that means the multiplicity is 2. Okay, so that 0 is showing up with a multiplicity of 2. All right, so now it says, what's the multiplicity of the larger 0? Well, the larger 0 is actually the number 5, because 5 is a larger number as compared to -3. So the answer here is going to be a multiplicity of 1. And now it's going to ask me, what's the multiplicity of the smaller 0? Well, the smaller 0 was -3. That had a multiplicity of 2. All right, now let's see this next question. It says the graph either crosses or touches the x-intercept, the x-axis at the larger x-intercept. All right, well, let me sketch out a little graph here, and I want to mention to you, what does multiplicity tell you about the x-intercepts? Okay, so let me sketch the x-intercepts here. Remember, we have an x-intercept at -3, and then we have an x-intercept over here at 5. All right, now, if a 0 has a multiplicity that's an odd number, like a multiplicity of 1 here, what that means is the graph is going to cross through. Let me come here to 5. It had a multiplicity of 1. What that means, the graph is going to cross through the x-intercept like that. If the multiplicity is 2, an even multiplicity like this, the graph is going to touch the x-axis and turn around. So the graph is going to do something like this. All right, so let's go to this question. It says the graph either crosses or touches at the larger x-intercept. Well, the larger x-intercept here was 5. It had a multiplicity of 1. That means the graph is going to cross at that x-intercept. How about the smaller x-intercept? That's -3. Well, because that had a multiplicity of 2, it's just going to touch the x-axis and turn around. It's not going to pass through the x-axis. All right. Here's another question. It says, what's the maximum number of turning points? Well, a turning point is where a graph turns around. So for example, if I had this kind of a graph, let's say, this is a turning point, because notice the graph was going uphill, but then it turned and goes downhill. Here's another turning point. The graph was heading down, but then it turned around and went up. And here's another turning point, and so on. Now, I could tell how many turning points there are without really graphing. The maximum number of turning points is always going to be 1 less than the degree. So 1 less than the degree. So I'd like to know, what is the degree of this polynomial function? Well, I remember the degree is the highest exponent. But this polynomial function isn't written in expanded form. It's just written in this factored form here. But I can see what the highest exponent is going to be. Imagine multiplying these parentheses out. When I multiply this parenthesis out, I'm going to end up with an x squared. And when I take that x squared and multiply times this x, I'm going to end up with x to the 3rd. So this polynomial is going to be degree 3. You could multiply it out if you want and check out the highest exponent, but we actually don't have to, because you can just imagine what would happen. Again, when I multiply this x plus 3 squared, that would be x plus 3 times x plus 3. I would end up with an x squared out of that. When I multiply the x squared times this first x in the parentheses, it's going to get me x to the 3rd. But remember, the number of turning points is 1 less than the degree. Excuse me, I should say the maximum number of turning points is 1 less than the degree. Our degree is 3, so the maximum here is 2. Okay, so the maximum number of turning points here is 2. All right, so now they're asking me to type in the power function that this graph resembles if x is very large? Well, they're really asking me here to type in the leading term. So remember, we know that if you were to multiply this all out, I would end up with degree 3, so that's x to the 3. But then that x to the 3 would get multiplied by -7, so I would end up with a leading term of -7. This leading term is going to tell you about the behavior of the graph. And we'll discuss this more when we get to graphing polynomial functions. But this leading term is important because it will tell you a lot about how this function behaves. Okay, so for this part D, they're really asking me to type in this leading term because that will tell me what happens to the graph when x gets very large or very small. So here I'm going to type in -7 x to the 3. All right, folks, hope these examples are helpful as you're working in section 4.1.